All right, pre-calc students, let's do a graph and analysis of a transformation of a tangent function. Up here at the top, I've got the general form of how you read the transformations of a trigonometric function. Wow, struggle. Okay, this number in front right here, we've got A, B, C, and D, which all do different transformations. A controls the vertical dilation and reflection. B controls horizontal dilation and reflection. Okay, and of course, this one would be vertical reflection over the x-axis, and this one would be horizontal reflection over the y-axis. And we've got C, which is horizontal translation, sliding left and right. And of course, remember that that says minus C because it works opposite of what you think it should. If you see subtracting a number, it actually moves it to the right. If you see adding a number, it moves it to the left. And then finally, we have D, which is vertical translation. Okay, so left, right, up, down, stretch and shrink horizontally and reflection horizontally. And then we have stretch and shrink vertically and reflection vertically. Okay, so in a nutshell, there's our general form. Now, specifically, we're going to look at the tangent of x and what happens if we put these numbers into that function and transform the graph. Okay, so out of all of these guys, what are they all doing? Well, the first thing I see is this negative sign out front, which is really, of course, a -1. And so that's going to cause reflection. And because it's outside the parent function, it's vertical reflection, which means over the x-axis. Okay, then we have inside the parent function, I have two things going on. And wait a second, though. I see that right now I have 2x minus pi over 2, but that looks different than my general form up here. There are no parentheses around the quantity of x minus pi over 2. So to me, that says that before I can analyze this function right here, I probably need to manipulate it, move the numbers around, and make it look like this general form up above. So I'm thinking, okay, well, I need a number to be out front and I need a plain old x right there. So that tells me I need to divide out 2. I need to factor a 2 off. Whoops. I need to factor a 2 off of those two terms. Okay, so what will that look like if I complete that work? Let's use a pen for this. Okay, so the front part's not going to change at all. The negative tangent of 2, okay, if I factored off that x, it's just going to leave me with an x. What happens if I divide negative pi over 2 divided by 2? Well, this is like negative 1/2 pi cut in half, so that's negative pi over 4. Okay, if you're unsure about that step, notice that you could distribute that 2 back in, and it should take you back to this original statement. That's what we just did, is we wrote it in factored form. Now we can finish our analysis and be sure that we're on the right track. So there's that negative sign again. That one didn't change at all. This number 2 is going to give us a horizontal dilation. Okay, and specifically, remember that the horizontal transformations work opposite of what you think they should. So by putting a 2 in here, my gut reaction goes, oh, that means it's going to be twice as big. But the horizontal dilation with a 2 actually causes a shrink. So shrink by a factor of 2. Okay, and then we've got this minus pi over 4. And so that one right there looks just like the C value up here, and it says minus. And so that means that I see this subtraction and it's working opposite of what I think. So that would be a horizontal. And that would be pi over 4 to the right. Okay, so there's the three things that are happening because of the values of those numbers that we put in there, the A, the B, the C, and the D. Okay, let's go do like we did last time, and let's start with some analysis of the period. Okay, so the period of the parent function. We know that the tangent of x has a period of pi. That means it repeats every pi units across the graph. And that's how much of the domain you have to graph to be able to see the entire pattern of the graph itself. Okay, well, now let's do the child period. Okay, to get the child period, I'm going to take the parent period and then perform the horizontal dilation on it. Okay, so I'm going to shrink it by a factor of 2. Well, that doesn't mean I'm multiplying it by 2. That means I'm cutting it in half. Either you can think about it as timesing by 1/2. Yeah, I really just said that. Multiplying by 1/2 or dividing by 2. Either way, it's going to get you to the same place that we now have a period of pi over 2. So half of what it was before. Now let's look at that interval calculation, the same one we were doing on the sine video. Okay, the parent initial interval for the tangent, the initial interval is from negative pi over 2 up to pi over 2. And the x lies between those values. And this time, unlike sine, when I did sine, I put equal to in there. But this time I'm not putting equal to because remember, these are the locations of the asymptotes on the tangent graph. So one full cycle of the tangent lies between these two values. Okay, how about the child initial interval? Okay, I'm going to take the endpoints of the parent, rewrite them in there, but this time instead of just writing x in the middle, I'm going to write the expression that was in here. And here's the cool thing. You can either write this expression as it originally looked, 2x minus pi over 2, or you can write it in its factored form, 2 quantity x minus pi over 4, and then close your parentheses. Either way should get you to the same initial interval for the child function. I think I'll write it just as it looks up here in the beginning. So I'll write 2x minus pi over 2. Okay, I want to solve for x in here. So that means I need to do a two-step inverse operations solving process. So I'm looking at minus pi over 2. I'm going to add pi over 2 to all three sides. Okay, and simplify. So these two combined up end up at 0. In the middle now, I just have a plain old 2x. Oops, sorry, running out of space. There we go. I'm adding pi over 2 to all the sides, the middle and the interval edges. And then, okay, 2x, there we go. And over here, I have pi over 2 plus pi over 2. That's a half a pi plus a half a pi, which gives me a whole pi. And now finish, divide both sides by 2. And I'll be left with 0 is less than x is less than pi over 2. There's my new interval for the transformed function. So the initial interval was from negative pi over 2 to pi over 2. The new one is from 0 to pi over 2. Let's see what that looks like on the graph. All right, so the original, the parent function, I'll put this in blue, but I'm going to do it with some dashed lines. The original parent function for tangent is from here to here. It has a point that passes through right there at the origin, and then it looks like curving up on this side and curving down on this side. Something along those lines, okay? Not perfect, but that's pretty close. Okay, there's the parent function. The new child has been shrunk by a factor of 2. So that means instead of having a full pi as its interval or as its period, it's half a pi instead. And remember that this also moved it pi over 2. Okay, just lost my brain. It has a horizontal translation, pi over 4 to the right. Okay, so that's why this function right here is ending up over here on the positive side of things this time. We are shrinking it in half and then sliding it to the right. So this new child function is going to lie right here between 0 and pi over 2. Okay, so hopefully you can kind of see that pink right there. Okay, now if these are the two asymptotes now, that means that the center of the graph should be halfway between them. It would be right here. And it's going to look something like this, but I'm not going to draw it in solid yet because we have another transformation left to go. Okay, so far, this pink dashed line right here is after we horizontally dilated by a factor of 2, shrunk it by a factor of 2, and then slid it pi over 4 units to the right. Finally, though, we do still have a vertical reflection in here over the x-axis, which means we're going to take this graph as it looks right now and flip it. So what was currently above the x-axis is going to flip down below, and what was below will become above. So after that reflection occurs, we'll go orange again, just like last time. There we go. That is a pretty decent transformed tangent graph. And of course, there's not just that one branch of it. You know that tangent occurs over and over again. It's periodic, just like all the other. Okay, I can't draw and talk at the same time, I guess. Just like all the other trigonometric functions. But really, we're just focusing on getting one interval in there to show where it shows up after all those transformations happen. Can we do any more analysis on this? Sure, let's do it. What else can we say about this graph? We can say that the amplitude, oh wait, a trig function does not have amplitude. It's not like the sine or cosine where it moves along in its wave form. There is no max and min height on an on a tangent graph, so there is no amplitude. Okay, what else do we have? We have reflection. Oh, you want to talk about reflection? Yes, we already talked about it, that there was a reflection over the x-axis. What else do we talk about? Okay, we talk about the domain. Okay, on a tangent graph, the domain, to describe it, usually I say, well, it's all real numbers except the places where the asymptotes exist. And so you just need to pick one of those asymptotes, like for instance, pi over 2. And then tell me how much you need to add or subtract to this initial asymptote to get the other asymptotes. So for instance, this asymptote is how far away from the other asymptotes? Oh, well, that's whatever the period is. The period is pi over 2. So we have a starting place of pi over 2, and then I can say plus or minus pi over 2 n. The n, remember, tells us, well, we talked about this before, I guess, in my class, but the n is an integer value, or I guess it could just be a whole number if you're going to use plus or minus. But this is saying that if you start at pi over 2, you can just have multiples of pi over 2 added on to that value and get all the possible asymptotes for that graph. The other way you could say this, I did notice we have an asymptote right here at 0, so you can make life even easier for yourself. And you could say instead of x equals pi over 2 plus or minus pi over 2n, you could even say 0 plus or minus pi over 2n, because that's another place where the asymptote is. Technically, you can pick any of these asymptotes and write this expression, but I do like to make life easy for myself. Both of those would be a correct statement for how to describe the domain. And then finally, do we have a range? Not a limited range. Our range is going to be from negative infinity up to infinity. And we do not include the infinities. We use our curved brackets or our curved parentheses because infinity is not a number. So we just say from negative infinity to infinity. No limitations on the range. Okay, so as far as I can tell, that's a pretty good investigation or analysis of this transformation of a trigonometric function. If you have questions, please email me. Don't hesitate. And yeah, have a good day. Have some fun with your trig. All right, bye-bye.